So good morning, students. Good morning, all. Are you hear my voice? Okay. Okay. So yesterday's class complete the pre-emphasis and de-emphasis networks. So pre-emphasis is the process which is used before modulation, and de-emphasis is used after modulation, after demodulation. Sorry. So pre-emphasis used before modulation. So de-emphasis used after demodulation. So why these and de-emphasis required in the improve the signal strength only. You need to improve the signal strength only. You required a pre-emphasis network. So at the transmitting end, used to enhance the signal strength by pre-emphasis network. So in general, the pre-emphasis network is nothing but high pass filter. High pass filter. Whereas in the whenever you use a pre-emphasis at the transmitting end, so the opposite network should be the de-emphasis network that is used at demodulation side. That is the receiver side. So the receiver side, you have to use the de-emphasis network. So the de-emphasis network is nothing but a low pass filter. The pre-emphasis network is high pass filter. The de-emphasis network is low pass filter. So students, please go through that material which is discussed in the earlier class. Okay, now, so you enter into another concept, that is a pulse modulation scheme. Pulse modulation scheme. So as of now, we completed analog modulation schemes. Those are amplitude modulation and angle modulation. So within the angle modulation, there is frequency modulation, phase modulation is there. So those are amplitude modulation and angle modulation. Both are analog modulation schemes. Both are analog modulation schemes. So another analog modulation scheme is a pulse modulation scheme. Another analog modulation scheme is a pulse modulation scheme. So why it is as analog modulation? So in the pulse modulation scheme is message signal is an analog signal. Always message signal is analog signal. Whereas in the amplitude modulation, the phase and frequency modulations, message signal is analog signal, that is continuous signal. Whereas the carrier is also carrier is analog in the nature. Carrier is analog in the nature in the amplitude modulation, frequency modulation. Carrier is analog in the nature in the amplitude modulation, frequency modulation, and phase modulation. But in the pulse modulation scheme, carrier is this pulse modulations. We are going to discuss about different types of modulation schemes. So those are pulse amplitude modulation, pulse frequency modulation, pulse position modulation. So can you define like amplitude modulation? The PAM is pulse amplitude modulation is so pulse amplitude, that is pulse used as a carrier now. Here you can use the pulse as a carrier. So pulse amplitude changes according to the modulated signal changes. Pulse amplitude changes according to the modulated signal changes, that is pulse amplitude modulation. It is also an analog modulation speed. So like the pulse width modulation. Pulse width changes according to the modulated signal changes. The width of the pulse going to be changed or going to be varied according to the modulated signal changes. What are the changes in the modulated signal? According to that, the width of the pulse should be the changes. So that is pulse width modulation, like pulse position modulation also. So that's why this pulse amplitude modulation, pulse position modulation, pulse width modulation, both are analog modulation schemes. So now we enter into the another concept here. We are discuss about another type of multiplexing of the process. So the earlier chapters discuss some sort of multiplexing. That is, multiplexing is number of signals are combined and those are propagated through a channel and you receive the signals at the receiving end. So while you are passing through the channel, the multiple signals are transmitting. Okay, so those are a multiplexing concept done at transmitting end and demultiplexing done at receiving end. So that's why in this chapter we are going to discuss one more type of multiplexing, that is uh, multiplexing of several signals is then achieved by interleaving of the samples of the individual signals. So the samples are interleaved. So then the signal going to be multiplexed. So this process we call as time division multiplexing. So because of with the reference of the time only, the samples going to be transmitting. So those samples are multiplex, then automatically signal also a multiplex. So since the sample is a pulse, so the system to be discussed are called pulse modulation schemes. Pulse modulation schemes. So now, so pulse amplitude modulation systems are analog modulation systems, and this is a common problem in AM and FM also. So that is, it is most extremely sensitive to the noise. So the pulse amplitude modulation or pulse width modulation, pulse position modulation, like AM and FM, it should be extremely sensitive to the noise presence in the receiver. So extremely sensitive to the noise, noise presence in the receiver. So now in this chapter we are also going to discuss about the conversion of analog to digital. Conversion of analog to digital. So because of the digital signals are less sensitive to the noise. Okay, where the analog signals are more sensitive to the noise. Digital signals are less sensitive to the noise. Okay, so now we're going to convert the analog signal into digital signal. So before digital signal, so that is conversion of analog to discrete signals. Analog to discrete signals. Okay. In the previous class also, this is one part of problem there. So the problem is, if you use 1 kHz telephone cable, may be expected to produce an attenuation of 1 dB per mile. So for that telephone cable, there is a attenuation of the signal 1 dB per mile. So such cable length is 3000 miles. Okay. Using that 3000 miles cable, the cable have attenuation at 1 dB per mile. 1 dB per mile. So if you expect 1 millivolt signal at the receiving end, what would be the signal at the transmitting end? Okay. So for that, there is a solution is at the transmitting end, there should be 10 to the power of 147 volt signal is going to be at the transmitting end, then the received signal should be 1 millivolt only. So that is huge amount of voltage is applied at the transmitting end. Is it possible? No, not possible. So that is, signals are more noisy in analog domain. When the signal is converted to digital domain, then the noise is at most reduces. Okay? So that's why you require digital systems to propagate clear signals. Okay, so you enter into the one of the concepts, that is conversion of analog to digital. One of the theorem is there, that is a sampling theorem. Sampling theorem. The sampling theorem says that already you know. So in practical, you find that signal to noise ratio of 40 to 60 dB are required for analog signals. In practical, you find that signal to noise ratio of 40 to 60 dB are required for analog signals, while 10 to 12 dB are required for digital signals. So this reason you went into the digital domain. Okay. Now, the sampling theorem. Sampling theorem. So this is outside the fundamental principle of digital communication. So this is outside the fundamental principle of digital communication is sampling theorem. So let M of t is the modulating signal or the baseband signal. Have it is band limited signal. Have it is band limited signal. And the frequency of FM. Frequency of FM. Let be determined at regular intervals of time. So that the values of M of t be determined at regular intervals of the time, and the time is Ts, that is sampling time, should be less than or equal to 1 by 2 FM. 1 by 2 FM. Yes, that is the sampling time for the regular intervals of the time of the M of t signal. M of t signal is a continuous signal. For the continuous signal, you can expect less than or equal to 1 by 2 FM. What is the FM? FM is the maximum frequency of the modulating signal, FM. So the 2 FM is, that is the twice. The spectrum is considered, that is 0 to FM is one side and 0 to minus FM is another side, the negative side. So overall the bandwidth is 2 FM. That's why the sampling time should be less than or equal to 1 by 2 FM. So TS should be less than or equal to 1 by 2 FM. At the time intervals, you can interval the M of the signal. So this is the signal is periodically sampled every TS second. Then the signal M of t is periodically sampled at every TS second. So then the samples, So M of t, the signal, after conversion of the samples, that is M of nTS. M of t should be converted to M of nTS, whereas n is an integer value. It is 0, 1, 2, 3, 4, like those. If n is equal to 0, that is the 0th sample. If n is equal to 1, the first sample. N is equal to 2, second sample. N is equal to 3, third sample, like this. That is, M of t can be converted to M of nTS, where nTS may called as the discrete signal. nTS may called as the discrete signal. M of t is a continuous signal. And the continuous signal is converted to discrete signal after applying a time samples, and the time samples period Ts should be less than or equal to 1 by 2 FM. 1 by 2 FM. So Ts less than or equal to 1 by 2 FM we called as sampling theorem. That is sampling time instance. So those are Ts nothing but the time instance. Sampling time instance. These are periodical sampling sample values. Periodically sample values. So now M of t is converted to M of nTS. nTS. So now the time Ts is called sampling time. So note that the theorem requires that the sampling rate be rapid enough so that at least 2 samples are taken during the course of the period corresponding to the high frequency spectral component. safety phase and spectral components. So please remember that, friends, TS should be less than equal to 1 by 2FM is the sampling theorem. TS is sampling time instance. So that process may be explained in this figure now. So if suppose MRT signal is considered, this is the MRT continuous signal, A bit, MRT continuous signal, and there is S of T, the sampling function contains the train of unit amplitude pulses are there. So the the B represent the S of T signal, that is, so unit sample pulse train, unit sample pulse train. The M of T, the modulating signal, that is a continuous signal, is a continuous in the time and continuous in amplitude, whereas S of T is the pulse train that is considered. Those two signals are applied to the multiplier. Those two signals are applied to the multiplier. M of T signal is one of the signal, that is continuous time signal. And S of T is a pulse train. When you apply to the multiplier output is S of T into M of T. The multiplier output is S of T into M of T. So now, where the S of T, then the signal is present. Where the S of T, the signal is present. So where if there is no S of T, the signal is absence. So the signal is present at S of T, the signal is absence, then the S of T is 0. So likewise, S of T is nothing but the time interval of the TS, and second pulse is 2TS, third pulse is 3TS likewise. So that is a continuous pulse train is applied to the multiplier with the magnitude of M of T. The samples are present with the modulating signal or continuous signal amplitude. So students, please be observe that this is 1, 2, 3, 4, 5, 6, 7. Like the samples are present now. Each sample, the first sample, what is the magnitude? Like the magnitude of M of T signal. Second sample magnitude, like the magnitude of the M of T signal. Likewise, these pulses amplitude varies according to the modulated signal changes. So this is nothing but a natural sampling. So this process may be called as PAM also. So because of the PAM is the pulse amplitude changes according to modulated signal changes. No? So now the A is M of T signal is applied to the multiplier, and S of T signal is applied to the multiplier, and output is S of T and M of T. This is continuous signal. Okay. Now the C is the multiplier, and D is the sampling of the signal M of T. So this is D is nothing but the sample signal of M of T. Now, the baseband signal M of T, which is sampled as shown in the figure, a period of pulse train, that is S of T is applied, which has unit amplitude. So, and the period is TS, as shown in the figure. The pulses are abruptly narrow, having the width dt, that is a narrow width, a small width. The two signals, M of T signal and S of T signal, applied to the multiplier as shown in the figure. So which the yield as output of the product of S of T and M of T. This product is shown in the figure, and M of T sampled at the occurrence of each pulse. M of T sampled at the occurrence of each pulse. So this is that is, when a pulse occurs, the multiplier output has the same value as does M of T. That is, when a pulse occurs, the multiplier output has the same value as does M of T. And at all other times, the multiplier output is 0. Okay. Now, so we now observe that the first term is series as M of T. The second term is M of T and having the frequency 2FM. Why can the 2FM means? So FM is the bandwidth frequency 0 to FM and 0 to -. So likewise, there is consider the spectrum is two-sided spectrum. So then you can consider that two-sided spectrum. This product, then a discussion of earlier double sideband suppressed carrier. So this is considered double sideband suppressed carrier signal with the carrier frequency QFM. Those who have used the FM is a spectrum. Now the QFM is double sided spectrum. That's why it is DSBS. Similarly, succeeding term yield DSBS series with the carrier frequency 4FM, 6FM, 8FM like this. So 2FM is a fundamental, 4FM, 6FM like this. This is the spectral component. Now, this is the signal. So A is nothing but the magnitude plot of the spectral density of the signal. The bandwidth is 0 to FM. So this is M of the signal spectral density. The spectral density, what is the maximum frequency? FM. So this is x-axis, there is a time, and y-axis there is a M of j omega mod, that is a transformation characteristics. Okay, so when this is plot of amplitude spectrum of sampled signals, 0 to FM is M of t, so that 0 to FM. Now 2FM, this is the first one. After that 4FM, 6FM, like this. So what is 0 to FM is one-sided, FM to 2FM, the another side, 2FM to 3FM. So now the spectrum is occurred at every 2FM time instant, 2FM, 4FM, 5FM. So what is the bandwidth now? 2FM and FM. It is 2FM minus FM. What is the span? FM only. So 3FM minus 2FM. What is the span? FM only. So the entire bandwidth is FM plus FM. FM plus FM. What is the bandwidth? 2FM. That is spectrum. So now this spectrum is occurred for multiple samples. So those the samples are present at 0 to FM and 2FM, 4FM, 6FM, 8FM, so on. So here you can observe one thing here. So 0 to FM is the span. 0 to FM is the span. At FM, second sampling starts. Second sample start. So 0 to FM and FM to 2FM, then 2FM to 3FM. So at the 3FM again, third one start. Okay. At 5FM again, fourth one start. So at the ending and starting time of the pulse, you know, look over this figure. So FM is the ending of the first, starting of the second. Like 3FM is the ending of the second, starting of the third. So likewise. So ending starting is there is the signal. So in this case, we call as TS is equal to 1 by 2FM. TS is equal to 1 by 2FM, not TS less than equal to 2FM. Less than equal to 1 by 2FM. This is TS is equal to 1 by 2F. So let the signal M of t have the spectral density M of j omega, that is Fourier transform M of t. M of j omega is can be calculated by using the Fourier transform, that is Fourier transform M of t, which is used M of j omega, which has the shown in the figure. Then M of t is band limited to the frequency range of 0 to FM. Okay. The spectrum of the first term extended to 0 to FM. The spectrum of the second term is symmetrical about the 2FM, and extended from 2FM minus FM. 2FM minus FM. What is the value? FM only. To 2FM plus FM. So that is 0 to FM can be extended to 2FM. Then 2FM minus FM means FM 2, 2FM plus FM. That is 3FM. So altogether, the spectrum of the sampled signal has the appearance shown in the figure, such that suppose then that the sample signal is passed through a ideal low pass filter. Suppose then the sample signal is passed through a ideal low pass filter with a cutoff frequency at FM. Cutoff frequency at FM. If the filter transmission were constant in the pass band and if the cutoff frequency were sharping at FM only, the filter would be pass the signal M of t and nothing else. So when the filter having the sharp cutoff frequency at FM, then the signal is going to be passed through a low pass filter. Otherwise, it's not. It's not. Now, so now the spectral pattern corresponding to above figure. So now we can show that another figure it is for the case in which the sampling rate Fs, whereas 1 by Ts is equal to Fs now. There are Ts is the samples, that is Fs is equal to 1 by Ts. So now the Fs is equal to 1 by Ts. So E is larger than 2FM. So now in this case Fs greater than 2FM. Fs greater than 3FM. So here it is. Fs is greater than 2FM. Fs is equal greater than 2FM. First figure A. The figure A says Fs greater than 2FM. At this case, what happens it is 0 to FM spectrum is there, and Fs minus FM spectrum no. Fs minus FM spectrum. So the ending and starting edges are not the same. Ending and starting edges are not the same. So between the ending and starting edges, there is a guard band is provided. Guard band is provided. This guard band is appeared with the Fs greater than 2FM condition only. Fs greater than 2FM condition only. The guard band is provided. So this is nothing but a sampling theorem. This is nothing but a sampling theorem. What is sampling theorem? Fs greater than 2FM. Fs greater than 2FM is nothing but the sampling theorem. So Fs is sampling frequency, that is nothing but 1 by Ts. That Ts is sampling time. So Fs greater than 2FM is the sampling theorem. So when the Fs greater than 2FM condition, there should be a guard band provided between the samples. The first sample, second sample, there is a guard band. Second sample, third sample, there is a guard band. Third to fourth sample, there is a guard band. So why these guard bands are required? So the guard bands are required to protect the signal. To protect the signal, guard bands are required. So and also, if you receive the signal, with these guard bands is able to identify samples clearly. Is able to identify samples clearly. If the guard bands are not there, then the identification of signals are not clear. So there should be some limitation occurred when guard bands are not there. So the guard band is there when that is clearly Fs greater than 2F. That is sampling theorem. So now another case you can see in the second B beta. Fs less than 2FM, what happens? Fs less than 2FM, what happens? If Fs less than 2FM, see that there is 0 to FM and Fs minus FM. So there should be an overlapping of the samples. Overlapping of the samples. Okay. See, this overlapping of samples occurred when Fs less than 2FM condition. Overlapping the samples occurred when Fs less than 2FM condition. So at this condition, signals may not be recovered at the receiving end. Fs less than 2FM condition, signals may not be recovered at the receiving end. So now this is not a suggestible formula for recovered signal. So only the recovered signal is possible at Fs greater than 2FM condition. So this is sampling theorem. So this is called as undersampling. Fs less than 2FM condition is oversampling, and the oversampling signals are not identified clearly and not recovered properly because of overlapping is done So when the overlapping is done, this process may be called as aliasing effect. When the overlapping is done, that process may be called as aliasing effect. So now this aliasing effect has occurred at Fs less than 2 condition. Fs less than 2 condition, there should be an aliasing. And the aliasing occurs, signals may not be recovered properly. So when Fs less than 2 condition, aliasing. So then the aliasing occurs, signals may not be recovered properly. So when the signals are recovered, Fs less than Fs greater than 2 condition, there should be recovered signal. So it is a sampling theorem. Okay. Now, so is a gap between the upper limit Fm to the spectrum of the baseband signal and the lower limit of DSPSC spectrum center around the carrier frequency Fs greater than 2Fm. Fs greater than 2Fm. For this reason, the low pass filter used to select the signal M of t need not have any sharp cutoff frequency. Need not be any sharp cutoff frequency because you have to apply for Fs greater than 2Fm condition. Okay, so the filter attenuate may begin at Fm but need not attain a high value until the frequency Fs minus Fm. So this range from Fm to Fs minus Fm is called guard band and is always required in the practice. So in the practice, always use Fs greater than 2Fm condition only. The practice use only Fs greater than 2Fm condition only. Okay. So a filter with infinitely sharp cutoff is not realizable. If suppose there is a voice signal, a limit of FM is equal to 3 point. One problem is that students, please be see that on probability. Fs is given as 3.3 kilohertz, while Fs is selected as 8K. Fs is selected as 8K. So then the guard band is, what is the guard band? Fs minus 2Fm. Fs minus 2Fm is the guard band now. So Fs is 8, Fm is 3.3. Fs minus 2Fm is, so 8 minus 2 into 3.3. That is 1.4 kilohertz is the guard band. 1.4 kilohertz is the guard band. So when you can see that another situation, that is Fs less than 2Fm condition. Fs less than 2Fm. Here you find an overlapping between the samples of M of t itself and spectrum of DSPSC signal. Okay, centered at Fs. Accordingly, no filter operating with allowing exactly the recovered M of t. Because of this Fs less than 2Fm condition, the no filter is realized to detect such a signals. So we have just found that sampling theorem, since we have shown that the principle, the sample signal can be recovered exactly when Fs greater than 2Fm condition or Ts less than 1/2Fm condition. So the sample signal can be recovered exactly when Ts less than or equal to 1/2Fm condition. It has also been shown by any minimum allowable sampling rate. The minimum allowable sampling rate is Fs is equal to 2Fm condition. Fs is equal to 2Fm condition is minimum allowable sampling rate. This minimum allowable sampling rate also may be called as Nyquist rate. What is the minimum allowable sampling rate? Fs is equal to 2Fm condition or Ts is equal to 1/2Fm condition. Fs is equal to 2Fm condition or Ts is equal to 1/2Fm condition. So there is a relation between Fs and Ts. So Fs is equal to 1/Ts. So that's why Ts is equal to 1/2Fm or Fs is equal to 2Fm condition. That is called as minimum allowable sampling rate or is called as Nyquist rate. Students, please be observed that it's an important relation. For the Nyquist rate, Fs is equal to 2Fm condition. That is minimum allowable sampling theorem. Okay, so An increasing sampling rate above the Nyquist state increase the bandwidth of the broadband. Okay, so thereby, so so now we go for one more concept, that is a sampling theorem. So the previous sessions we discussed the sampling theorem. Please go to the sampling theorem from here onwards. This is sampling theorem. You can use that plots and M of the signal and S of the signal is given to multiplier, and then go to the now we go for one more concept, is a multiplexing concept. So there are two types of multiplexing. One is time division multiplexing, and one is frequency division multiplexing. So in this one, by using the sampling principle, so like an example, there is M1, M2, M3, M4, M5, M6 are the signals, are independent signals. M1, M2, M3, M4, M5, M6 are independent signals. So using a commutator to select, so one after other, those signals are passed through communication channel. This is a single communication channel. Those are received at the receiving end. At the receiving end is the decommutator. So decommutator having the select independent signals as a commutator release. So there is 1, 2, 3, 4, 5, 6 signals are there. Whenever the signals are propagating, and those signals are at the transmitting end, the same signals are received at the receiving end. So when the signals are released by using the commutator, and signals are receiving by using decommutator. Commutator and decommutator. Commutator is at the transmitting end, decommutator is at the receiving end. The decommutator use a filters. Filter 1, filter 2, filter 3, like this. How many signals are there? Such number of filters are used here. Okay. So now this is the band limited signals are or a single communication channel. So now at an example. So there is M1 and M2 are the signals. M1 is, this is the signal, dotted line, and M2 is another signal. This is the signal. When the samples are created, the M1 sample is the first sample, and M2 sample is. So M1, M2 are the two analog signals are sampled by using the sampling time. The M1 signal is appeared at first one, M2 signal appeared at second one. Like the second sample, this is the first signal sample, and this is the second signal sample. So like third sample, this is the third signal sample, this is the second channel, third signal sample. So you can observe that each signal have 1, 2, 3, 4, 5, 6 number of samples are there, like the first signal samples and second signal samples. So the other sampling time instance are between the successive samples, first sample to second sample to third sample, like that. That is the TS time. The time is the same. So when these samples are propagated through a channel individually, we observe that the train of pulses corresponding to the samples of each signal are modulated in amplitude in accordance with the signal itself. Accordingly, the scheme of samples is called pulse amplitude modulation and abbreviated as PAM. So the samples are amplitude varies. So that is scheme is imposed here. So the amplitude of the samples are changes according to modulation. That is pulse amplitude modulation. So the multiplexing of several PAM signals. One signal have one PAM. That is, each signal have its own amplitude domains. And here in the example, there are two signals are there. The first signal have its own samples, that is not the PAM, And second signal also its own amplitude. That is that is also PAM. Now this is the multiplexing of several PAM signals. Now these are the two PAMs used here because of the two signals are there now. So multiplexing of several PAM signals is possible because various signals are kept separately, recovered by various factors. They are sampled at different times. Hence, this system is an example of time division multiplexing. Time division multiplexing. Because of the time TS samples, signals are going to properly. Such systems are counterparts in the time domain of the system of TDM. So the signals are kept separately by virtue of their translation of different portions of frequency domain, and the frequency is used as a frequency domain, and those systems may called as frequency division multiplex. Frequency division multiplex. Okay. So students, so go to the topics which are covered until now. In the next class, go for natural sampling onwards. So I sent a material to you. So go to the material and please follow this concepts. Okay, thank you, one and all.